Imagine for a moment you're standing right at the edge of some fast, complex machine. Maybe it's a really bustling train yard, with dozens of lines all intersecting, or perhaps it's a brand new high-speed rail network stretching across hundreds and hundreds of miles. Trains are moving at incredible speeds, signals are constantly changing, and beneath it all, there's this intricate web of tracks, power systems, digital controls. It's all humming with activity. The sheer scale is breathtaking, isn't it?
It really is.
But here's the critical question, the one that, keeps engineers up at night. How do we make sure that these incredibly complex systems, everything from, say, the individual wheels on a train to the really elaborate signaling infrastructure, are not just working, but are reliably functioning day in, day out?
Right.
How do we guarantee they're always available when needed, easily maintained when issues pop up, and, most crucially, safe for everyone involved? When lives are literally on the line, how do we predict potential failures before they even start to happen, and then make truly smart, proactive decisions about safety and uptime?
That's really the core challenge, isn't it? It's a question that moves far beyond just, reacting to a problem once it occurs.
Yeah.
It's about building in foresight, resilience, predictability right from the ground up. And this is precisely where the field of RAMS comes into play.
RAMS.
RAMS, yeah. It stands for reliability, availability, maintainability, and safety. These four pillars, they aren't just abstract concepts. They are, the bedrock of modern engineering, particularly in these high-stakes environments like railways, where even a tiny malfunction could have pretty catastrophic consequences.
Absolutely. And you might think, okay, well, we have basic reliability calculations, right? We learn those. But here's the thing. For the incredibly intricate, interconnected systems that define today's railway industry, and honestly, any complex modern system you can think of, those basic, simple RAM analysis methods, they just aren't enough anymore.
No, they really aren't.
You can't just sketch out a basic diagram, run a few numbers, and expect to capture the full picture of risk and performance. The world is just too dynamic, too intertwined for that kind of approach.
Precisely. Simple failure rate calculations, they fall woefully short when you're dealing with systems that don't just abruptly fail, but might sort of degrade gracefully over time or have multiple layers of redundancy where backup components kick in.
Right, like a slow decline.
Exactly. They also struggle with complex human-machine interactions, the nuances of maintenance schedules, or situations where the sequence of events truly matters. What we really need are methods that can truly model system evolution, quantify that inherent uncertainty, and dissect the intricate web of dependencies. It's about moving from a binary on-off view to a much more nuanced understanding of system health.
And that, my friend, is precisely what we're embarking on today. Our mission for this deep dive is to explore 4 incredibly powerful advanced modeling techniques that help us navigate this immense complexity.
Okay.
We'll be diving into Markov models, Monte Carlo simulations, and Bayesian networks, each offering a unique lens to peer into system behavior. And we'll also touch on Petri nets, which is a really visually intuitive way to model concurrent processes.
Sounds good.
So, if you're an aspiring engineer listening, or maybe a seasoned professional looking for new tools, or perhaps just a railway enthusiast curious about the cutting edge of safety, get ready for a fascinating journey. I'm genuinely thrilled about unpacking these sophisticated tools that are literally shaping how we build and manage some of the world's most critical infrastructure.
And these advanced methods are truly indispensable because they empower engineers to move beyond that simplistic fail or not fail perspective.
Yeah.
They enable a really detailed, predictive understanding of how systems evolve through different operational or degraded states, how uncertainties propagate throughout a complex network of components, and how intricate interdependencies can lead to unexpected, sometimes dangerous outcomes. This level of insight is absolutely crucial for robust RAMS analysis and, maybe most importantly, for making truly informed, proactive decisions that save both money and lives.
Okay, let's unpack this with our first powerful tool, Markov models. At their heart, Markov models are a quantitative technique used to describe how a system's state evolves over time. To grasp their core principle, think of it like this. Imagine you're playing a board game, right? And your next move only depends on the square you're currently on.
Right, just the current position.
Exactly. It doesn't matter if you got there by rolling a double 6 3 turns ago or by picking up a go back 3 spaces card. Just where you are now dictates what happens next. That's the key concept, what we call memorylessness, or the Markov property.
Yeah, and that memoryless property, it's not just some mathematical curiosity. It's incredibly powerful for reliability and safety analysis. It dramatically simplifies what could otherwise be an overwhelmingly complex analysis because it means you can focus entirely on the immediate transitions from the current state.
Oh.
You don't need to trace back the entire historical path of the system. This allows for a much more tractable analysis, especially for systems where components fail and are repaired, or where specific sequences of events or states really matter. For a railway engineer, what this fundamentally allows you to do is precisely quantify the long-term reliability and availability of systems with moving parts and repair crews, truly predicting system evolution and identifying weak points under stress without drowning in, irrelevant historical data.
So if I'm a railway engineer, how does that memoryless property translate into a game-changing implication for my work? It seems almost counterintuitive for something like, I don't know, an aging train component. Doesn't its history matter?
That's a really great question, and it points to a common misconception, actually. While a physical component does have a history of wear and tear, of course,
Right.
what the Markov property allows us to model is that, for predictive purposes, if we define our state accurately enough, perhaps component is worn but functional, component is degraded, or component has failed, then the probability of its next transition can often be effectively modeled based only on that current state.
Ah, I see. So the state captures the relevant history.
Exactly. It simplifies the problem to a manageable level by focusing on the transition rates between well-defined states. It means you can build incredibly robust predictive models without getting buried in mountains of irrelevant historical data, allowing you to optimize maintenance schedules and predict future failures with surprising clarity, assuming those transitions are time-independent or can be averaged out reasonably well.
So why are Markov models so ideal for RAMS, especially in a field like railways? Where do they really shine?
Well, they are particularly useful for systems with built-in redundancy.
Mm-hmm.
Think of, say, a backup signaling unit that kicks in if the primary one fails, or maybe a redundant power supply for a critical railway junction.
Yeah.
They also excel at modeling situations where the system failure depends on the sequence of individual component failures, not just that they failed in isolation. Furthermore, they're exceptionally well suited for systems with complex operation and maintenance strategies, such as cold standby components where a backup is unpowered until explicitly needed.
Right, sitting there waiting.
Exactly. Or scenarios with prioritized repair actions and maybe limited resources for corrective maintenance. And critically, they allow us to model multi-state systems. Many real-world railway components, like a section of track or maybe a train's engine, they don't just abruptly fail.
Yeah, it's not just on-off.
Right. They might degrade, operate in a reduced capacity, or enter various states of degraded performance before complete breakdown. Markov models can map all these nuanced states quite effectively.
I love how these models can be visualized. It's not just a bunch of, intimidating equations. There's a real intuitive diagrammatic approach. We use something called state transition diagrams, which are incredibly helpful for understanding the system. You essentially have circles, which are your states, like system working perfectly, component A failed, but B is still going, or maybe system completely down. And then you have arrows connecting these circles, representing the transitions between states, like component A fails or component B is repaired.
Mm-hmm. And each arrow has a rate associated with it.
Right, indicating how quickly that transition happens.
Exactly. And by analyzing these diagrams, or rather by solving the underlying mathematical equations that describe these transitions, you can obtain a wealth of information. You can calculate measures like instantaneous availability, which is the probability of the system being operational at a specific moment in time,
Okay.
or steady state availability, which tells you its long-term average operational probability. You can also get the average availability over a specific period, the mean operating time to the first failure, and the mean downtime for repairs.
Wow, lots of useful metrics.
Yes. And for functional safety, these models help compute crucial measures like dangerous failure rates.
Yes.
So how often the system fails dangerously, and the average probability of failure on demand, which is critical for safety-critical systems that are only activated occasionally, like an emergency braking system.
That visualization is so powerful. It makes me wonder, though, what's underneath that visual simplicity? How does the math actually make those transitions tick? Without getting bogged down in intense equations, what's the sort of simplified theoretical background here?
Conceptually, well, the magic happens in how we describe the probabilities of moving from one state to another. For a system where random failure and repair times of its components are independent and follow an exponential distribution, which is a powerful and often reasonable assumption in many reliability analyses because of its memoryless property.
The memoryless thing again.
Right, it links back. A homogeneous Markov process is an excellent fit in those cases. While other distributions can be approximated, doing so significantly increases the model's complexity due to what we call state-space explosion.
State-space explosion. Sounds dramatic.
It can be. Imagine trying to map every single possible combination of 1,000 train components being on or off, working or degraded. The number of possible states quickly becomes astronomical, just too big for even the most powerful computers to analyze directly.
Okay, yeah, I can see that.
Essentially, the probability of being in any given state at a future time can be derived by solving a system of differential equations that describe the constant transition rates between states. These rates are fundamental to how the system moves from one state to another over time.
Let's make this concrete with a simple example that builds our intuition. Imagine a parallel system with just two components, A and B. Both need to fail for the entire system to go down. So if one fails, the other can still keep things running, maybe in a degraded state, but running.
Right. A good, simple case. Let's walk through 3 scenarios to build intuition. Case 1. No repair. Absorbing state. So here, components fail, and once failed, they cannot be repaired, ever. You start with both A and B functioning. Let's call that state 1. If A fails, you move to a state where A has failed, but B is working, state 2.
Okay.
If B fails first, you move to a state where B has failed and A is working, state 3. Critically, if both A and B fail, you reach a system failure state, state 4. Now, this system failure state is what we call an absorbing state, because once you enter it, there are no arrows leading out. You can't leave.
It's stuck there.
Exactly. The probability of being in this absorbing state over time directly gives you the system's overall failure probability. It's like a black hole for your system's functionality.
So once it's failed for good. No coming back. That really brings the stakes to life. Very clear.
Correct. Now let's look at case 2, partial repair, system functioning. Let's introduce repair capabilities, but only when the system is still functioning in some capacity. So if component A fails, but B is still working, state 2, you can repair A and transition back to both components function in state 1.
Ah, okay. You can recover.
Yes. Similarly, if B fails, but A is working, state 3, you can repair B and return to state 1. But, and this is key, once the system fails, both A and B are down, state 4, no more repairs are possible, and it remains an absorbing state.
Still a black hole if both go down.
Right. This adds transitions back to the functional states from the degraded states, clearly showing how maintenance strategies can improve system reliability and uptime by pulling the system back from the brink, as long as it hasn't totally failed.
So you can fix things, but only if the system hasn't completely collapsed. What about if you can fix it even after it's totally down? Does that change the nature of the model?
It absolutely does, and profoundly so. That leads us to case 3, full repair, irreducible Markov process. In this scenario, we allow for repair even after system failure. So if both A and B fail, state 4, you can still repair them, bringing the system back to a functional state, state 1, or perhaps an intermediate degraded state first, then back to state 1.
So there's always a way back.
Exactly. This creates what's called an irreducible Markov process, meaning you can eventually reach any state from any other state. The system is truly resilient, always able to recover and find a stable operational rhythm over time, theoretically.
That sounds much more hopeful.
It reflects repairable systems. In such systems, the probabilities of being in each state will eventually stabilize over the long term, leading to what we call limiting or stationary distributions. For example, you can calculate the steady state availability, the proportion of time the system is expected to be up and running in the very long term.
Okay.
In this context, the probability of being in a failure state at any given instant represents the system's instantaneous unavailability.
That's a brilliant way to visualize the progression from total failure to, well, true resilience.
Yeah.
So if an engineer needs to develop a Markov model in practice, what structured steps do they typically follow? It's not just drawing circles and arrows randomly, I assume.
No, definitely not. It's a structured process, not a shot in the dark. First, you define your precise objectives. What exactly do you want to measure? Is it transient behavior over a short period, like the probability of failure during a specific mission, or long-term steady state values like average availability? Do you have repairable components, or is it a one-shot system?
Got it. Step 1, goals.
Step 2, you critically verify if Markov modeling is actually suitable. This means checking if component failure and repair times are independent and can be reasonably assumed to be exponentially distributed, or if other distributions can be sufficiently approximated without making the model explode.
Right, the suitability check.
Third, you carefully identify all the necessary states to fully describe the system for your analysis. This might involve various operational modes, specific failure modes, recovery states, maybe even common cause failures that affect multiple components simultaneously.
Define all the possibilities.
Fourth, consider if any system symmetries allow you to simplify the model by combining identical or equivalent states. This helps mitigate that state space explosion we talked about. It's about being clever with the model.
Okay, simplify where possible.
And finally, step 5, you set up the transition matrix, which mathematically defines all the possible moves between states and their rates. Then you evaluate the model to get your quantitative results, interpret what they mean for your system, and document everything thoroughly for future reference and verification.
Define, verify, identify states, simplify, set up, evaluate, interpret, document. Seems logical. And are there any advanced extensions or nuances to these models that push beyond the basic homogeneous Markov process?
Yes, absolutely. The field is constantly evolving. Beyond the basic homogeneous Markov process, there are semi-Markov processes, which are incredibly useful because they relax the assumption of exponentially distributed times and states, allowing for arbitrary time distributions.
So not just exponential.
Right. This is often more realistic for complex maintenance processes. And then there are Markov reward models, which incorporate reward functions for being in certain states or for specific transitions.
Rewards, like points.
Sort of. It allows for the calculation of broader performance measures beyond just uptime, such as average maintenance costs over the system's lifespan, or even the expected revenue generated while the system is in a particular operational state. This demonstrates the immense adaptability of the method beyond just pure reliability numbers.
Here's where it gets really interesting for our listeners, I think. How are Markov models actually applied in the railway industry? Give us some specific real-world uses that highlight their power.
Oh, they're used frequently and with significant impact. For instance, they're employed to describe the deterioration and critical damage accumulation of railway track assets over time.
Like wear and tear on the tracks.
Exactly. Helping engineers investigate how different asset management strategies, say, different inspection frequencies or repair thresholds, impact the long-term health and availability of a railway track section. They're also used for modeling the reliability and availability of rolling stock, like a specific type of train, under very complex maintenance strategies, taking into account scheduled servicing, unscheduled repairs, component lifespans, the whole 9 yards.
Okay.
And on a larger scale, they're used for assessing the overall reliability and safety of entire railway transportation systems, looking at the interaction of multiple subsystems working together.
Can you give a quick conceptual example?
Sure. Imagine a discrete time Markov chain modeling a railway facility's states, say a critical switch junction. Its states could be something like safe and fully available.
Yes.
Safe but unavailable due to maintenance, unsafe but fully available due to a latent fault, or maybe unsafe and unavailable due to a critical failure.
Okay. Those 4 states.
You could then track how the probabilities of these unsafe states change over time based on defined transition probabilities, like the probability of fault occurring or the probability of a maintenance action completing successfully. This directly informs risk assessment, allowing us to predict the likelihood of an unsafe condition developing over a shift or a month, and then prioritize interventions accordingly.
So what are the big strengths and, conversely, the practical limitations of Markov models when you're trying to apply them in the real world?
Okay, strengths. They include their exceptional capability to describe complex redundancies and the dynamic behavior of multi-state systems. They can provide a wide array of measures from instantaneous to steady-state reliability and availability. Plus, those state transition diagrams are a simple and intuitive means for visualizing and communicating the model's underlying structure, which makes it easier for diverse teams to understand.
Easier to get everyone on the same page.
Definitely. However, the main limitation is that numerical evaluation can be incredibly intensive. And as we discussed, they can suffer severely from state space explosion.
Right. Too many states.
Exactly. This means for very complex systems with many interacting components, each with multiple failure modes, the number of possible states can become astronomically unmanageable, making the model computationally infeasible. This often limits their practical application in very large-scale, highly detailed scenarios unless clever simplification techniques are applied.
Okay, moving on from that more abstract state-based view, let's talk about Petri nets, or PNs. This is another powerful modeling technique, and its strength, as I understand it, lies in describing a system's global behavior by modeling its local states and events.
It's a good way to put it.
What's really cool about them is their highly graphical, intuitive nature, using what we call tokens to represent the flow of activity. It's kind of like watching a dynamic flowchart come to life.
Yes, PNs are particularly relevant for RAM purposes, especially a variant known as Generalized Stochastic Petri Nets, or GSPNs. In GSPNs, random times are introduced to represent the duration of events like failures or repairs.
Stochastic, meaning random.
Right. Now, while GSPNs can theoretically be represented as Markov models, meaning you can convert one into the other, they often offer a much more compact and visually intuitive representation, especially when dealing with highly concurrent and parallel processes, which are incredibly common in railway systems. Think of multiple trains operating simultaneously, or several maintenance crews working in parallel on different parts of the system.
Lots of things happening at once.
Exactly.
So what are the basic elements of these GSPNs? How do you actually draw one out? What are the building blocks?
You'll typically see three fundamental components. First, there are places which are drawn as circles. They hold tokens, usually shown as dots, and these tokens literally describe a local state or condition, for example, component working, train at station, or signal is red. The combination of all tokens in all places at any given moment is called the marking, which represents the global system state.
Okay, circles are places holding tokens for local states.
Got it. Second, you have transitions, which are rectangles or bars. These represent events that cause a change in the system's state, like a failure occurring, a repair completing, or a train departing. If it's an exponentially distributed random event, it's typically an outlined rectangle.
Yeah.
If it's an immediate deterministic event that happens instantly when enabled, it's often shown as a solid bar.
Places and transitions, what connects them?
That's the third part. Directed arcs. They are arrows connecting places to transitions. These are input arcs, or transitions to places. These are output arcs, showing the relationships and the flow of tokens. An input arc specifies how many tokens are required in a place for a transition to fire or occur.
Like a prerequisite.
Exactly. An output arc specifies how many tokens are put into a place after a transition fires. If no number is indicated on the arc, the default is usually one token. You can also have more sophisticated extensions like inhibitor arcs.
Inhibitor arc.
Yeah, they disable a transition if a certain number of tokens are present in an input place, essentially preventing an event from happening if a specific condition is met. Think of it as a safety lock. Or testing arcs, which check for tokens without actually consuming them. These extensions are crucial for modeling complex interdependencies and safety interlocks in real systems.
Okay, so you have places, transitions, arcs, tokens moving around. How does a Petri net model actually play out? What are the rules of the game, dynamically speaking, to see how a system behaves over time?
It's like a simulation on paper, or in software. It starts with an initial distribution of tokens across its places, which we call the initial marking, representing the system's starting state.
Okay, the starting setup.
Then, a transition is considered enabled when all of its input places have the required number of tokens, as specified by the input arcs. Once enabled, it fires after its specified time delay, which could be a random duration for a stochastic transition, like a failure time, or immediate for a deterministic one, like a control signal.
So it waits its time, then fires.
Right. When a transition fires, tokens are removed from the input places and added to the output places, according to the arc, multiplicities, the numbers on the arcs. This process then repeats continuously, modeling the system's dynamic behavior over time as tokens flow through the network.
And you mentioned a key difference from Markov models.
Yes, the key notational difference is subtle but powerful. In PNs, places represent local states or conditions, and the combination of tokens across all places defines the global system state. This often makes it far more compact and intuitive for modeling highly concurrent or parallel systems where many things can happen simultaneously.
That makes a lot of sense. So it handles parallelism more naturally. And how do engineers construct these PN models in practice? Is there an iterative process like with Markov models, or is it more free-form?
No, it's quite structured and often iterative, similar in spirit to Markov modeling. First, you identify the system boundaries, its main components, and their functions. What are you actually modeling?
Scope it out.
Second, you model the structure modularly, often creating smaller, manageable submodels for different functions, specific dependability aspects, or control mechanisms. These submodels are then linked together, often using those special arcs like inhibitor or testing arcs to represent interdependencies.
Build it piece by piece.
Third, you rigorously check and refine the model until it reaches the desired level of detail and accuracy for your analysis objectives. Does it capture the behavior correctly?
Check and refine.
Fourth, you analyze the model. This could be either qualitative, looking at properties like reachability, can this bad state ever happen? Or liveness, can the system get stuck? Or quantitative, obtaining stationary or transient performance results like throughput or availability.
Analyze it.
Finally, you visualize, interpret, and thoroughly document the analysis results. There are even extensions like colored PNs, which attach properties or data values to tokens, allowing for even richer and more complex modeling, for instance, distinguishing between different types of trains or signals within the same model.
That sounds incredibly versatile and very powerful for visual thinkers. Where do we see Petri nets applied in the railway industry? Can you give us a concrete example?
They are particularly powerful for describing distributed and concurrent complex railway systems where multiple independent processes interact. A classic and very clear example is modeling traffic at a railway level crossing.
Okay, the crossing.
You can distinctly model two concurrent processes. One for the train, which might have states like outside the danger zone, approaching, or inside the danger zone, and another for cars, with states like outside approaching, inside the danger zone, waiting at barrier.
Two separate flows of tokens.
Right. Petri nets can beautifully model their interactions, including critical safety mechanisms. For example, you might use an inhibitor arc to prevent the car enters danger zone, transition from firing if there's a token in the train approaching or train in danger zone place.
So the train prevents the car from entering.
Exactly, it models that interlock. Such models can rigorously highlight potential accident scenarios. For instance, if the sequence of events isn't perfectly controlled, maybe a train entering while a car is already present, even with prevention mechanisms designed in, it really shows the flow of interactions that can lead to hazardous states.
So how do Petri nets compare to Markov models then? You mentioned earlier they can represent Markov models but are often more compact. What's the key advantage there?
That's a crucial point. While generalized stochastic Petri nets can indeed be represented as underlying Markov models, meaning every GSPN have a corresponding Markov chain you could theoretically draw out,
Right.
Petri nets are frequently far more compact and visually manageable for systems with a high degree of concurrency and parallelism. This is because a single Petri net diagram can implicitly represent a very large Markov chain state space in a much more visual and condensed form.
It hides the complexity better?
In a way, yes. For instance, if you have multiple components that can fail and be repaired independently, a Markov model might need a distinct state for every single combination of their operational status. That state space explodes fast. A Petri net, however, can represent each component with its own simple subnetwork, and the tokens movement captures the overall system state more elegantly. This makes them often better suited for modeling the practical complexities encountered in highly concurrent systems, where the state space explosion for a direct Markov model would become prohibitive.
All right, let's shift gears completely now to a different beast entirely, Monte Carlo simulation. This is a fascinating technique that, for me, always brings to mind repeatedly rolling dice or running many what-if scenarios for a complex project thousands or even millions of times over.
Yeah, that's a good mental image.
It's all about embracing randomness and repetition to help us understand overall probabilities and behaviors. It's a powerful stochastic simulation technique.
That's a great analogy. Monte Carlo simulation works by repeatedly solving a model, using randomly sampled input variables and events, and then statistically treating the outcomes from these multiple independent runs. Its immense power comes from its ability to inherently account for uncertainty and to tackle systems that are simply too complex to solve using traditional analytical techniques like direct mathematical formulas.
So it's for problems you can't just calculate directly.
Exactly. It's like getting answers to questions that can't be solved with a simple equation by just trying it out many, many times and observing the results. It's the ultimate trial and error approach, you might say, but executed with computational rigor and statistical analysis.
So how is this repetition and randomness specifically used in the RAMS context? What kinds of problems does it solve for us in reliability and safety?
In RAMS, Monte Carlo simulation is often a lifesaver. It's used to evaluate incredibly complex fault trees or even Markov models where failure times or state durations follow arbitrary probability distributions. They don't have to be just exponential, which is a major advantage over traditional Markov models.
So any distribution works. That's huge.
That flexibility is game-changing. It's used to estimate measures like mean operating time between failures, or the precise probability of failure within a specific time interval, even if the system's behavior is highly nonlinear or driven by non-standard distributions. It also helps estimate cumulative density functions in risk assessment. For example, when you need to know the average availability within a warranty period, or perhaps a value that should only be exceeded with a given very low probability, like a safety threshold.
Okay.
Furthermore, it's flexible enough to model highly complex operation and maintenance scenarios where state changes occur at discrete time instants, capturing this sort of nuanced choreography of real-world system management.
A core part of this seems to be generating those random inputs correctly. How do you get realizations of random variables that follow really specific and complex probability distributions, not just, a simple uniform random number from a spreadsheet function?
Right, you need the right kind of randomness. That's where the statistical ingenuity comes in. Conceptually, there are two main methods for generating these specific random variates from basic uniform random numbers, which computers are good at generating. The first is the inverse transform method.
Inverse transform.
Imagine you have a cumulative distribution function, CDF, for your desired variable. That's a curve that smoothly goes from 0 to 1, representing the probability of a variable being less than or equal to a certain value.
Okay, the S-shaped curve, often.
Typically, yes. If you take a uniformly distributed random number between 0 and 1, you can find the corresponding point on the vertical axis, the probability axis, of this curve. Then trace horizontally across to the curve, and then straight down to the horizontal axis, the value axis. That value on the horizontal axis is your random variate, magically transformed to follow your desired, often complex, distribution. It's like having a special ruler that transforms simple uniform numbers into numbers that perfectly fit your desired pattern.
That makes perfect sense, sort of mapping the uniform randomness onto the shape you want. And what if that curve, that distribution function, is too complex to invoke mathematically easily, if you can't easily solve for the value given the probability?
Good question. Then you might use the acceptance-rejection method. Imagine you want to generate numbers from a very strangely shaped, irregular distribution, something that looks like a lumpy hill, maybe hard to describe with a neat formula.
Right.
What you do is generate numbers from a simpler, easier to sample distribution that completely covers or encloses your target distribution, perhaps a simple rectangle drawn around the hill. Let's call this the proposal distribution. Then for each number generated from this simpler proposal distribution, you throw a dart, which is basically generating another uniform random number between 0 and 1. You scale this dart relative to the height of the proposal distribution versus the target distribution at that point.
Okay.
If the dart lands below your target distribution's curve at that point, you accept the generated number because it falls within the desired shape. Otherwise, you reject it and try again with a new number from the proposal distribution. It's like throwing darts at a complex shaped target drawn inside a rectangle and only keeping the darts that land inside the target shape. It effectively filters for the desired distribution, even if it can be computationally intensive because you might reject a lot of samples.
That helps visualize it beautifully. Throw darts, keep the ones inside the weird shape.
So with these random variates in hand, what are the basic concepts of how Monte Carlo actually works to estimate something, like an average failure time, from all these repeated runs?
Well, the fundamental idea is deceptively simple, actually. You estimate an expected value, like an average failure time, an average cost, or an average availability by generating many, say, n independent samples from your model. You run the simulation n times, each time drawing new random inputs using methods like the ones we just discussed.
Okay, and runs.
You then simply take the average of the n outcomes from those runs. This average, which we call an estimator, will approximate the true expected value of the system. The good news is that the accuracy of your estimate intuitively improves as you increase the number of samples.
More rolls of the dice, better average. Precisely. This is thanks to the powerful statistical concept called the law of large numbers. More specifically, the standard deviation of your estimate, a measure of its uncertainty, decreases, typically with the square root of the number of samples. This allows you to compute confidence intervals, giving you a statistically rigorous sense of how accurate your result is. For example, we are 95% confident that the true mean time to failure is between X and Y. This also applies directly to estimating probabilities. You simply count the number of successes, e.g. the system failed within the mission time, out of n simulations and divide by n.
But what if n has to be enormously large to get sufficient accuracy, especially for really, really rare events like catastrophic failures? You might need billions of runs. That could make simulations incredibly slow, potentially impractical, right? Is there a way around that?
You've hit on a critical challenge, especially for safety analysis, where we care about very low probability events. And that's precisely where variance reduction techniques come in. These are a suite of clever statistical methods designed to achieve more accurate results with fewer simulations.
Fewer simulations, same accuracy. Sounds like magic.
It's not magic, it's smart statistics. They essentially reduce the statistical uncertainty or variance in your estimate without needing to dramatically increase the number of runs. This is achieved by incorporating some form of existing information about the problem into the simulation process, rather than just relying on pure brute force randomness.
Techniques include.
Okay, what are some examples?
Well, there's importance sampling. This involves biasing the samples towards rare but important regions of interest, for instance, deliberately making rare failure events occur more frequently in the simulation, but then mathematically correcting for that bias during the calculation. So the final estimate is unbiased.
Yeah.
It's like rigging the dice to land on 6 more often, but then adjusting the score later so it's fair in the end. But you learn more about rolling 6s with fewer rolls overall.
Clever. What else? There's correlated sampling, or common random numbers. This is incredibly useful for comparing small changes in a system, like in sensitivity analyses.
Right.
You use the exact same sequence of random numbers for slightly different system configurations. This cancels out a lot of the random noise and helps you isolate the effect of the change more clearly.
Okay.
And things like subset simulation, which refines simulations iteratively based on information from previous broader samples, effectively narrowing down the search space for rare events and stages.
So these speed things up.
They can significantly reduce the number of runs needed. The trade-off, however, is that while you significantly reduce variance and overall computation time, you often increase the computational cost per simulation run and, critically, the programming effort required to implement these sophisticated techniques. They are not trivial to set up correctly. You need to know what you're doing.
Okay, time for some real-world railway applications. Where is Monte Carlo simulation making a big, tangible impact in the railway industry?
A very specific and profoundly impactful application is in computing correction factors for emergency brake deceleration curves within the European Train Control System, or ETCS framework.
ETCS braking curves.
Okay, this is absolutely crucial for ensuring sufficient safety margins, given the natural statistical dispersion of braking performance, for example, how much a train might vary in its braking on dry rails, which is represented by a factor sometimes called K-dry. These correction factors need to ensure safety with an extremely high emergency brake confidence level, sometimes as high as 1-10 to the power of -9, 1/10 to 9.
Wow, that's incredibly high confidence, like 1 in a billion chance of failing that standard.
Exactly. Due to these incredibly high confidence levels, simple Monte Carlo simulations just won't cut it. You'd need an impossible number of runs. So variance reduction techniques and specialized estimation procedures for these extreme quantiles become absolutely essential.
Makes sense. Any other uses?
Oh, yes. It's also widely used in general railway risk analysis to quantify uncertain events and to model uncertainties in component reliability characteristics. For example, instead of assuming a single fixed failure rate for a component in a fault tree model, you might say the failure rate is uncertain but lies somewhere within a range, perhaps following a uniform distribution. Monte Carlo lets you propagate that uncertainty through the entire system model, giving you a range of possible outcomes for the system failure probability, instead of a single, often misleading point estimate. It gives you a feel for the variability.
So what are the big strengths and, on the flip side, the practical limitations of Monte Carlo simulation when you're thinking about using it for RAMS?
Okay, strengths. Its main strengths are truly remarkable. It offers incredible flexibility to account for virtually any type of probability distribution for input variables, not just the exponential ones often required by basic Markov models.
That flexibility again.
Huge advantage. It provides solutions for complex systems that simply cannot be solved analytically using direct mathematical formulas. And crucially, it also provides a measure of the accuracy of its results through confidence intervals, so you know how much trust to place in your findings.
You get error bars, essentially.
Exactly. However, its limitations are also significant. The accuracy heavily depends on the number of simulations performed, and for very precise results or extremely rare events, and can become astronomically large, even with variance reduction. Convergence can be painfully slow sometimes.
There's a long time to run.
It can. And often, it requires significant programming effort and specialized statistical knowledge to set up, run, and interpret the simulations correctly. It's a powerful hammer, but you really need to know how to wield it properly, especially when using those advanced variance reduction techniques.
Okay, let's move to our final, incredibly powerful tool. Bayesian networks, or BNs, and their extension, influence diagrams. These are truly fascinating. I think of them as incredibly smart, probabilistic graphical models, essentially networks of nodes, which are like random variables or factors that affect a system connected by directed links or arrows that show dependencies or even causal relationships between them. It's like a flow chart, but for probabilities and influences.
That's a perfect way to describe it. The nodes in a Bayesian network represent random variables, and each variable has a finite set of possible mutually exclusive states, for example, component working or component failed, or maybe train speed high versus train speed normal.
The different possibilities for that factor.
Exactly. And the directed links truly represent the dependency structure. Often they indicate a causal relationship, like brake failure causes accident, but not always. Sometimes it's just correlation. What's crucial here is that each child variable in the network, one that has arrows pointing to it, has a conditional probability table, or CPT, attached to it.
CPT, conditional probability table.
Right. This CPT defines the probability of that child, variable states conditional on the states of its parent variables, the ones with arrows pointing from them to the child. For example, if poor track maintenance is a parent of derailment risk, then the CPT for derailment risk will show different probabilities depending on whether the poor track maintenance state is true or false.
So the table shows how the parents influence the child.
Precisely. If a variable has no parents, no arrows pointing to it, it's a root node, and it simply has unconditional prior probabilities, its baseline likelihood of being in each state.
So how does information or evidence flow through these networks? You mentioned something called deseparation, which sounds a bit technical but seems important for how they work. Can you give me a very quick everyday analogy for how information might flow or not flow in a simple scenario?
Absolutely. Deseparation is the concept that describes how evidence or information transmits or is blocked through the network based on the connections and the states of intermediate nodes. There are three basic patterns to understand.
Okay, pattern one.
First, serial connections, where variables are in a chain, like A influences B and B influences C. Think, A, rain, makes B, ground is wet, makes C, risk of slipping. Information flows from A to C through B if B's state, wet ground, is uncertain. If B's state is known, say you've looked outside, know the ground is wet, then learning it rained. A tells you nothing new about the risk of slipping. C, beyond what you already knew from B. The information flow is blocked at B once B is observed. Okay, knowing the middle step blocks the flow. Makes sense. Pattern 2. Second, diverging connections, where one parent influences multiple children, like A influences B and A also influences C. Think, A, faulty signal, make as B. Train 1 passes red light, and AC, train 2 enters same block. Information transmits between the children B and C if the common parent A state, faulty signal, is uncertain. If you observe train 1 passing the red light B, it makes it more likely the signal is faulty. A, which in turn makes it more likely train 2 will enter the block. But again, if A's state is known, the signal is confirmed faulty, then observing B tells you nothing new about C. The flow between B and C is blocked by knowing A.
Knowing the common cause blocks the info between effects. Got it. Third pattern.
Third, converging connections, where multiple parents influence one child, like A influences C and B also influences C. Think, A, high train speed, miss C, derailment, and B, track defect, miss C, derailment. This one is unique. Information transmits between the parents A and B only if there's information about the child variable C, derailment, or one of C's descendants. If C derailment is unknown, the parents A and B are considered independent. Learning the train speed was high tells you nothing about track defects and vice versa.
Oh, okay.
But if you observe the child C, a derailment happened, then the parents suddenly become dependent. Learning that the train speed was high, A, now makes the probability of a track defect B less likely because the derailment has now been partially explained by the high speed. This is called explaining away. This structure allows the calculation of the joint probability mass function of all variables in the network by multiplying all the conditional probabilities together, capturing the overall probabilistic state of the system and how evidence changes beliefs.
That's incredibly insightful. It really changes how you think about causality and evidence, especially that explaining away part. So BNs are used for three main tasks, right? Building the network, figuring out the probabilities, and then using it to answer questions based on evidence.
Precisely. The three main tasks are interconnected and often iterative. 1. Structural learning, SL. This is about determining the network's topology, figuring out which variables are linked and in what direction, which arrows to draw. This can be done based on expert knowledge of the system, or increasingly learned directly from vast amounts of data using algorithms.
Building the map.
2. Parameter learning, PL. Once the map is known, this task involves determining the unknown probability parameters within those conditional probability tables, CPTs. How strong are the links? Again, this is typically done from historical data or through expert elicitation.
Filling in the numbers on the map.
3. Probabilistic inference, PI. This is where you actually use the built and parameterized network to compute probability values for variables given some observed evidence. This is the what-if engine, the reasoning part of the BN.
Okay, let's dig into that last one, probabilistic inference. How does it answer those crucial what-if questions for engineers? What can you do with it?
PI allows you to perform two critical types of analysis. First, you can predict, for example, ask, what's the probability of a specific outcome, like a system failure, if X happens, like a particular component degrades? This often uses the total probability theorem, propagating probabilities forward through the network from causes to effects.
Predicting the future based on inputs.
Second, and perhaps even more powerfully, they can estimate or diagnose, for instance, asking, what's the probability that X happened, a specific cause, given that Y was observed, a symptom or failure? This is where Bayes' theorem truly shines, allowing you to calculate posterior probabilities, updating your belief about causes based on observed effects. The posterior probability of X given Y is proportional to the likelihood of observing Y if X were true, multiplied by the prior probability of X. This is the inverse logic, going from effect back to probable cause.
Diagnosis, finding the likely cause.
Exactly. These questions are answered using various algorithms. For smaller, discrete BNs, exact methods can compute precise probabilities. However, for larger, more complex or continuous BNs, approximate simulation-based algorithms are often necessary. Methods like direct sampling, rejection sampling, or more advanced techniques like Markov chain Monte Carlo, MCMC, can handle continuous variables, avoiding the need for discretization, although assessing the accuracy of these approximate methods can sometimes be more challenging than for exact methods.
This sounds incredibly powerful, and it reminds me of classical reliability tools like fault trees and event trees. Can these established methods be incorporated into Bayesian networks, or do BNs sort of replace them?
That's one of the most compelling aspects of Bayesian networks, actually. Fault trees, FFTs, and event trees, ETs, which are foundational in reliability and safety analysis, can be seamlessly and directly converted into Bayesian networks. They don't replace them, but rather subsume and extend them.
Ah, so you can translate them.
Yes. For fault trees, basic events like component failures and logical gates like AND or OR, which define how component failures combine to cause a system failure, the top event, become random variables and conditional probability tables in the BN. This is a significant advantage because BNs overcome several fundamental limitations of classical fault tree analysis.
Like what?
Well, BNs can model more than just binary pass-fail states. You can have degraded states or multiple levels of failure. They can inherently handle dependent events where the failure of one component influences another, which is tricky in standard NFTs. And they can even represent non-coherent systems, which are systems that use logical gates beyond just AND/OR, like XOR, exclusive OR, or NOT gates, which classical NFTs struggle with.
More flexible logic.
Right. Similarly, event trees, which model sequences of events leading to different outcomes following an initiating event, also map very well into Bayesian networks, providing a more flexible and dynamic representation where you can update probabilities anywhere in the sequence.
That's a huge benefit, unifying these classical tools. And when you map these, how do the elements from fault trees and event trees actually translate into the different types of nodes in a BN? Is there a clear classification?
Yes, there's a very clear and intuitive classification when you map them. Root nodes of the BN typically represent the basic events from fault trees. These are your fundamental causes like component A fails or human error occurs. In event trees, root nodes represent the initiating event itself, or the technical or operational barriers and neutralizing factors that act to prevent or mitigate an accident sequence.
Barriers and neutralizing factors? What's the difference?
Think of barriers as active mitigators that prevent a hazard from escalating, like an automatic braking system designed to stop a train before collision. Neutralizing factors, on the other hand, mitigate the consequences after a barrier has failed, such as emergency responders arriving after a derailment has already occurred. Both become root nodes influencing the outcome.
Okay, what about other nodes?
Intermediate nodes correspond to the intermediate events or logical gates in fault trees, the steps between basic failures and the top event. And event trees, these represent intermediate scenarios or pivot points in the accident sequence, outcomes of barrier functions.
And the final nodes.
Finally, leaf nodes are the ultimate outputs of the network model, meaning the top events in fault trees. Example, system failure, derailment. Or the various consequences in event trees, sample no damage, minor damage, major accident. This mapping provides a unified, powerful framework where you can model causes, effects, intermediate steps, and protective barriers, and then perform inference in any direction, prediction, or diagnosis.
And BNs have an even more advanced extension, right, called influence diagrams, or IDs. What do these add to the picture beyond just probabilities and dependencies?
You're right. Influence diagrams are a critical extension of Bayesian networks that incorporate decision-making directly into the model. They introduce two additional types of nodes on top of the regular BN nodes.
Okay, what are they?
First, decision nodes, which are usually drawn as rectangles. These represent choices or actions that an agent, like an engineer or manager, can take, such as implement maintenance schedule A or schedule B, or upgrade signaling system now, or wait.
The choices you can make.
Second, utility nodes, which are often diamond-shaped. These represent outcomes, values, or costs. Essentially what you are trying to optimize. It could be minimizing total cost, maximizing safety level, maximizing passenger satisfaction, or some combination.
What you care about, the goal.
Exactly. Okay. Influence diagrams model what's called prior analysis, where decisions are optimized to maximize the expected utility, the average value of the utility node, based on all available probabilistic and statistical information from the BN part before any action is taken. This is incredibly useful for making optimal choices in complex railway scenarios, where the best decision often involves balancing safety measures with operational costs, aiming to maximize overall value or minimize risk. For example, deciding whether to invest in a more robust but expensive component versus a cheaper, less reliable one, while explicitly considering the long-term maintenance costs and potential accident costs predicted by the network.
Let's revisit a conceptual example from the railway world. A train derailment accident is a nightmare scenario. How would a Bayesian network model this incredibly complex situation, linking all those different factors we've discussed?
It's an ideal application for BNs, precisely because of that complexity and the dependencies. A BN can effectively model the multitude of various factors contributing to a derailment and their complex interdependencies, which are rarely simple linear relationships.
Okay, like what factors?
For instance, you could have nodes for things like high train speed, sharp curve and track alignment, driver errors like distraction or fatigue, poor track maintenance like worn rails or bad geometry, train protection and warning system, TPWS fails, or component fatigue in wheels or axles.
Lots of potential causes.
And the relationships between these factors, like how high train speed and sharp curve and track alignment might combine to significantly increase the probability of a speed and alignment issue, are precisely modeled by those conditional probability tables we discussed. The BN can then calculate the overall probability of the top event, the derailment itself.
And it can update.
Yes, crucially, it can update that probability dynamically with new evidence. If you observe that the TPWS failed during an incident, for example, the network can immediately update the probabilities of other related factors. For example, perhaps making driver error less likely to be the primary cause if the TPWS should have prevented it but failed, and the overall derailment probability. This diagnostic capability is invaluable for comprehensive functional safety analysis, root cause analysis after an incident, or even for proactive risk assessment, helping engineers pinpoint the most effective intervention points to reduce risk, even if a real-world model would be far more detailed than this simplified sketch.
So, what are the overall strengths, and on the other hand, the practical limitations of Bayesian networks and influence diagrams that engineers need to be aware of when considering them?
Okay, strengths. They are incredibly powerful for modeling and handling uncertainties and complex dependencies in risk and decision-making problems, offering a really holistic view of a system. The dependency structure among variables is clearly visualized, which makes it intuitive to understand and easily communicated, which is critical for multidisciplinary teams working on safety.
The visual aspect is strong.
Very strong. And perhaps most powerfully, updating probabilities with new evidence is mathematically straightforward and conceptually intuitive. You just instantiate or fix the state of an observed node, and the network immediately updates all other probabilities based on Bayes' theorem.
Easy updating is key. Limitations.
Limitations include that BNs and IDs are usually built with discrete variables. This means continuous variables like temperature or vibration levels often need to be discretized into ranges, for example, low, medium, high, which can introduce approximations and might lose some information.
Chopping up continuous things.
Right. Also, modeling dynamic problems where things change continuously over time is harder. It typically requires discretizing the time axis itself into a limited number of time slices, creating what are called dynamic BNs, DBNs. This can become quite complex to manage and can suffer from its own kind of state explosion in the time dimension, though it's different from the continuous time Markov model issue. So they're less naturally suited to continuous time dynamics than Markov models. # summary and final thoughts.
Wow, what an incredible deep dive into some truly advanced techniques. We've covered a lot of ground. To recap, we've looked at 4 powerful tools today that are really revolutionizing how we approach reliability, availability, maintainability, and safety in complex systems like railways.
Indeed. We started with Markov models. Remember, these are excellent for understanding how system states evolve over time, especially when dealing with redundancy, repair, and complex maintenance strategies. And those intuitive state transition diagrams make them surprisingly accessible, right?
Absolutely. Then we looked at Petri nets, which are fantastic for visualizing and modeling concurrent behaviors and parallel processes. They can often represent complex systems more compactly than Markov models, particularly where many things are happening at once.
Our third tool was Monte Carlo simulation, the ultimate tool perhaps for embracing uncertainty. It offers incredible flexibility, handling pretty much any input distribution and providing solutions for systems too complex for analytical methods, though we noted it can be computationally intensive and requires careful statistical rigor.
Yeah, the flexibility is key there. And finally, we explored Bayesian networks and influence diagrams. These are the champions for managing uncertainties, complex dependencies, and integrating decision-making directly into risk analysis. They truly help us reason about cause and effect when information is incomplete or uncertain.
And this brings us to a really crucial point. There's no single method that is universally superior. You can't just say, always use Markov or always use a Monte Carlo.
No silver bullet.
Exactly. The best choice always depends on the specific characteristics of the problem you're trying to solve. You need to consider the nature of the system. Is it highly concurrent? Does it have strict repair policies? What type of uncertainty are you dealing with? Are failure times exponential or something else? Do you need dynamic behavior over time or just long-term stationary solutions?
Matching the tool to the job.
Right. For instance, Markov models might be more intuitive for systems with clear states and known exponential failure repair rates, especially involving redundancy. Petri nets are often better for highly concurrent systems, where timing and sequencing of parallel tasks are critical. Monte Carlo offers maximum flexibility for distributions and complex logic, but comes with a higher computational cost and programming effort. Bayesian networks excel in handling uncertainty, dependencies, and integrating evidence, but are perhaps less naturally suited for continuous time dynamics or finding long-term stationary solutions without complex extensions.
It's also worth explicitly noting, as you touched on, that these methods aren't mutually exclusive. Far from it. They often complement each other, and you can even combine them for even more robust analyses.
That's a very important point.
For instance, you might use Monte Carlo simulation to analyze a complex Markov model where the equations are too hard to solve directly, or to simulate a large Bayesian network to estimate probabilities. The interconnectedness of these methods often yields far more robust and comprehensive analyses than using just one in isolation.
Exactly. It's about building a multifaceted toolkit, knowing the strengths and weaknesses of each tool, and sometimes using them together.
So why should you, our listener, whether you're an engineering student, an early career professional, or maybe a railway safety enthusiast, care deeply about these sophisticated models? Well, if you're an engineering student, these are foundational tools for real-world problem solving, equipping you with methods to analyze truly complex systems that you'll undoubtedly encounter in your career.
They really move beyond textbook examples.
For early career professionals, understanding these methods can give you a significant competitive edge in ensuring the safety, efficiency, and resilience of critical infrastructure. It allows you to contribute at a higher level. And for railway enthusiasts, it deepens your appreciation for the incredibly sophisticated engineering that goes on behind the scenes every single day to ensure safe and reliable transport. These tools move us beyond simple pass-fail assessments to quantifying how likely something is to fail and what's the impact if it does, allowing for truly proactive rather than reactive safety management.
And in a world of increasing complexity and ever-demanding safety standards, the ability to not just react to failures, but to anticipate them, quantify their risks, and make proactive, data-driven decisions is absolutely paramount. So here's a thought. Consider how might these advanced modeling techniques, often hidden away behind the scenes in complex software tools, be subtly shaping the safety and efficiency of the very next train journey you take, or the next complex system you encounter in your daily life. They are often the unseen guardians of reliability.
That's a powerful thought to leave with. We encourage you to think about these models in your own fields, whatever they may be, to look for opportunities where a quantitative understanding of reliability, availability, maintainability, and safety could make a profound difference. These tools aren't just for academics in ivory towers. They are practical, powerful instruments in the modern engineer's toolkit, ready to be applied. Thank you so much for joining us on this deep dive today.
Thank you. It was a great discussion.